So let's go ahead and get started here. So first of all, for those on the call that may not know much about Hamilton Kent, we have about 70 years of experience in the industry supplying a variety of different types of rubber sealing products, including gaskets for manholes, box culverts, pipe. We also manufacture a variety of different variations of rubber flexible connectors for pipe to manhole connections. But we've been working with the industry in a variety of different ways for that long. We have a very experienced and innovative engineering and technical as well as sales staff. A lot of experience with the company as well as within the industry. So it's a lot of people to draw on for help with our customers. We are ISO 9001 and 14001 certified at both of our locations, the one in Toronto, Ontario, and in Winchester, Tennessee. So just a demonstration to our commitment to safety, to quality, as well as to environmental concerns. So just this might be a little bit small on your screen, so I apologize for that, but just a quick schematic that shows the different varieties of sewers and water distribution that we're going to, I'm not going to be talking about all of this, but I thought this is just a nice way to start to kind of show where it all starts with the water, coming in on the distribution lines here. You have water mains coming into the houses. You also have rainwater that comes out of storm systems. And where all that water then goes, whether it's into a storm sewer, a sanitary sewer, a combined sewer. So this is just a schematic that I like to show just to kind of show how it all wraps together. And then the next graphic, I think it's helpful then to see more of a detailed view of what are the different products that are used in sealing that infrastructure. So obviously this is going to be for a sewer line, not for water distribution, but for sewer lines, really broad variety of different types of products, from anywhere from the top, the watertight frame and cover, chimney seals, all the way down to repair couplings, connectors, gaskets of a broad variety, even PVC and type pipe gaskets. So these are all types of gaskets that we work with in the industry. So why gasketed joints? I think that's really the big question. So the first bullet point I put here, I think, is one, and I think it's very important, and that is increasing specification by government agencies. And we're certainly seeing that more cities, more counties, more state DOTs are requiring gasketed joints just because they see the value of that in making sure that they have watertight connections. An example would be now Tennessee DOT. They require on all their pipes for it to be gasketed and no longer accept butyl sealant. Installation is relatively simple, and I say that depending on which type of gasket is used. Obviously, if they use a pre-lubricated gasket, that's going to be the simplest route to go. There are also a regular gasket with lubrication. That would be probably the middle of the road type of installation. One picture I have shown here is a butyl sealant being used on a manhole. Butyl sealant is also very easy to install, but it also is messier. It's sticky and catches dirt, so it's a little more of a challenge to use. But those are three of the options that are most popular for sealing a joint. We think the gaskets are a better performing joint, remains watertight regardless of any type of movement within the joint. So if after installation, if there's differential loading on a pipe, then gaskets are going to be able to handle that and close, to basically maintain any type of connection, even if there's a slight gap in the joint. Whereas a sealant like a butyl sealant may not have that type of capability. Contractor friendly, we feel that gaskets are, for the most part, very contractor friendly. We do hear from issues from time to time of a gasket not being installed correctly. Or forgetting to use lubricant when they should, or using it when they shouldn't have. But for the most part, gaskets are very user-friendly. Backfill, faster backfill certainly is going to be the case when you compare to like a mortar joint. If the contractor is having to mortar each joint and having to maintain or keep that trench open long enough for that mortar to solidify, then that's going to slow down the project. And we'll talk about that more here in just a minute. So just a couple of reasons why gasketed joints are so good. Just some of the joint basics. First of all, I think probably a lot of this is very, very logical, but the manufacturer of the pipe, the manufacturer of the box culvert, or the manhole, whatever the structure is that has a joint on it, must supply a joint and a gasket, or whether it's a butyl sealant. They must meet the specifications on the job. So if it's ASTM C443 for a stormwater project, they're required to make sure that whatever they send to the job site, whether it's the structure as well as the gasket, it has to meet those requirements. And then the next part of that is the field performance of any joint. Really, it comes down to three things. One is the joint design. Is it a joint that's going to be able to, basically to handle the requirements of the standards? The quality of the joint, so the quality that's manufactured in the plant, is it going to be good enough to meet those standards? Then it's going to be, the next one's going to be the rubber gaskets. Are the gaskets, are they the right size? Are they the right type, the right material to meet those requirements? And then the third factor is the care with which the gasket and the unit are installed and handled at the job site. So those are what we feel are three very important issues and considerations when it comes to joints and gaskets. Unfortunately, we do see pictures like this one in the bottom right there, where you do have the leakage of through a joint like that. Oftentimes, that's because either the gasket was not put on the joint, or because the gasket was unfortunately became dislodged before the installation was finished. But unfortunately, the joints are just usually the weakest point in the system. And we do have heard of pipe leakage, but that is relatively rare unless it's a pressurized pipe. There are simple steps that can save cost of repairs, and there's quality assurance steps that plants can take. There's quality assurance steps that gasket manufacturers take in order to prevent something like this happening. But it also can be factors, as I mentioned before, about what happens at the job site. Contractors do like a good price, and there's no doubt about that, because this being a price-driven market, so heavily price-driven, that the lowest bidder is who gets the job. So they're always going to be looking for a good price, but they also want some reassurance that when they install the pipe and they install the gasket, that the joint is going to perform properly, because they know that if it doesn't perform properly, that eventually that's going to be a cost to them in another way. So contractors do have some reason for making sure they have quality on the job site as well. Municipalities and engineers are becoming more critical. I think that this is, as we're seeing infrastructure become so much bigger focus all the time, like the ASCE, American Society of Civil Engineers, just released the report card on the infrastructure, and we have a D+ rating overall for the United States. So that's showing that how much challenge we're facing with the infrastructure. And then municipalities, they've got limited budgets, and they have so much work to do, so they're going to be really paying attention closely to the quality of the work that's being done. So here's the problem we see virtually everywhere we go. I mean, every city you go to, you're going to see manholes that look like this, and where the pavement is starting to crack, it's starting to sink, and this is really due to the fact that there's leakage within the pipe, or within the pipe to manhole structure connection, and that's the fines, the ground around the manhole are starting to erode, and the pavement starts to sink. So this is something that a lot of cities are facing, and this is something that can be avoided. Here's some everyday headlines. I mean, you probably have seen some of these yourself, and there's certainly a lot more of them out there. But is the U.S. infrastructure destined to crumble? I mean, certainly we're seeing examples of that. But I think that everybody knows that. I mean, everybody knows that infrastructure is important and needs to be rehabilitated. So I think steps are being taken in the right direction, but it's still happening all around us. Maybe just the fixes aren't being done at a fast enough pace. And then you have bigger failures like this one, which I'm sure a lot of people saw this one. I think this was last year in the parking lot of a brand new IHOP. It was a storm sewer, and it had a leaking pipe, and it eroded the ground around the pipe, and eventually the whole thing failed, and that caused a major collapse like this. So, just a watertight storm sewer joint is so critical, and unfortunately, a lot of municipalities still don't realize the importance of keeping stormwater sewer watertight as well. They figure that stormwater is draining off anyway with with a little extra water that's caught in it. Well, this is what can happen. You can have a major failure like this. So now let's talk about 3 different types of joints, and I say RCP for reinforced concrete pipe, but this also applies to manhole structures as well as box culvert. So the first one, tongue and groove, then confined O-ring, and then single offset. So first of all, tongue and groove. I mean, you've got pictures at the bottom, and there are different types of varieties of tongue and groove joints, but this is the most common. It's very easy to manufacture. There are generally I'm not going to say a loose tolerance, but it's not as strict tolerance that you have to meet as far as manufacturing goes. So it tends to be the easiest to manufacture. Installation is fairly easy. Putting butyl sealant on a joint like this and homing it is fairly easy. There are challenges, of course, making sure that the butyl is installed in the right location and things like that. Gaskets can be used with a tongue and groove joint, but however it is limited. And as I noted here, the slope of the joint has to be 5 degrees or less in order for it to be glued in place so that it'll seal correctly. There are a lot of, I'd say most manufacturers of tongue and groove joint products, their joint is going to be more than 5 degrees. So we get calls pretty frequently asking about a gasket for something that's for a joint that's greater than 5 degrees of slope, most of them being 10 degrees up to even 15 degrees. Unfortunately, there's really nothing on the market that we have either developed or that our competitors have that really works well. And it's just because as the joint opens up, the connection between the bell and the gasket gets lost too quickly, and so all it takes is just a small gap in that joint, and you'll have a leak. So it's just not really effective. Here's an example of a gasketed, a tongue and groove joint for a box culvert, and it's a very good example. Nice straight lines, a very smooth joint. So this would be a very high quality tongue and groove joint. I talked a minute ago about grouted pipe joints. A lot of times these are just tongue and groove joints, and then rather than using butyl, they just use a mortar, and they mortar all the joints. And unfortunately, most of the time that we are aware of this or see this is out west, where there's more seismic activity. And so, you got 2 issues. Number one is you can't backfill this trench until the mortar's dry. Number 2 is if there's any type of movement in the ground, any type of seismic activity, any type of differential loading, that grout is going to crack. It doesn't take a whole lot for grout to crack. And as soon as that crack is formed, that water's going to start leaking in there. And that just creates more issues like what we've already talked about. The O-ring joint is next, and that would be the joint that years ago was developed, and many years ago was developed, just because it had excellent water tightness and very high pressure resistance. You still see that used to some extent, and not as much as it was years ago. A lot of companies have switched to the single offset joint now, but you still do see some O-ring joint, especially if it's going to be any type of pressure pipe. The gasket is closely confined, and we'll talk more about this here in just a moment, but you can see this groove right here where the gasket would sit, and so it's confined in that space, and that's what creates the pressure between that space and then the bell coming over it. It is more challenging to manufacture, which is one of the reasons why a lot of manufacturers have gone away from it, just because in order to make it, you have to have a snap ring on your formwork, and then you have to remove the pipe or remove the manhole from that formwork, and then you have to carefully take that snap ring off without chipping the corners of that confined groove. Because if you chip that, and it could mean that you're going to lose the water tightness. That the gasket could roll out of that joint, or just won't seal as well. So it is more challenging to manufacture. Installation is also a factor. There are a few steps involved with putting a gasket on and then homing that pipe. So it is more challenging for the contractor as well. And then very tight tolerances. I mean, it's extremely tight tolerances to manufacture this because there is such a in order for the joint and the gasket to work properly, there's not a whole lot of variation you can have in that joint to have it perform well. And then, as I just mentioned, the single offset joints. I mentioned the first bullet point, manufacturing is easier, but that's because even though it is easier because you don't have that snap ring to deal with to make that confined O-ring, there are still tight tolerances in order to perform well with a gasket. Installation is simplified, and that is just simply because you don't have to do nearly as much, there's not nearly as much labor involved with installation of the gasket, and it usually goes together when homing the pipe or homing the manholes. It goes together a little bit better, a little bit easier. Very good water tightness and pressure resistance. It may not be as high, certainly not going to be as high as an O-ring can go, but certainly single offset joint will meet C361 requirements of 13 psi. There are a broad spectrum of gasket types which will work with single offset joint, which is another benefit. So there's lots of opportunities, lots of choices for producers as well as for contractors. So here are some single offset joints on a variety of different structures. You have round pipe on the left with a super seal pre-lubed gasket on it. In the middle you have a manhole with a wedge-shaped gasket on it. And on the right you have, again, a super seal gasket, this time on a gasketed box culvert. So all those with single offset joints. And then you also can do use a gasket on non-round pipe. So these are, again, have single offset joint. First one you have arch pipe, and then on the right you have elliptical pipe. And it seems to work very well with, especially with a pre-lubed gasket, just because it helps with the kind of centering the pipe when you're homing it. So as I mentioned, there are a variety of different types of gaskets. Here's just a couple of them that were available. Here are some profiles of some that you'll see. The one here on kind of the top left, that's going to be a pre-lubed gasket, the red being indicating where the silicone lubricant would be inside of the rolling tube. You have obviously an O-ring gasket over here. You have a variety of different types of gaskets with a notch in the back. This is, it's supposed to be to help with areas where it's going to be maybe higher water table, so you're going to have more external water pressure. So those pockets help to expand the gasket when there's external pressure. So I just wanted to point these out just because there are a variety of different types of gaskets that are available. Obviously, the O-ring is not going to be one of those options for single offset, but that just does show the different types of gaskets. So how do you choose between gaskets? First of all, I think, if from the producer standpoint, is what type of tooling do you have? So maybe you have single offset tooling already, and so that's going to give you a lot of options. But it could be all you have is single offset is going to be all you're going to have is a confined O-ring joint, and then your options are going to be limited either to continuing to go with an O-ring gasket or to going with new tooling to create a single offset joint. So that's going to be the first step. From a contractor and engineer standpoint, a lot of times it's going to be what is offered by your local producers. So if there's our pipe producers in your market that are making single offset joint on pipe or manholes, then obviously there's a lot of different options, but there are some areas that they still require O-ring gaskets, and so it's going to be a confined O-ring groove. What does the market expect and is willing to try? So contractors in general are pretty kind of set in their ways. So a lot of times they have what they know what they want. They want butyl sealant, or they want a pre-lubed gasket, or they want something else. But some markets, contractors are willing to try something new. I mean, that's what happened with Super Seal 25 years ago when it was first introduced into certain markets. Contractors, they found they really liked it, and they ran with it. So it's really going to just depend on what the market is willing and able to do. And then what characteristics are most important. So if it's going to be really high water table and there's going to be a lot of pressure, or is there going to be water flowing through the pipeline that's going to be contain contaminants? Or is there going to be, there's a variety of different factors it could be. So what characteristics are most important? So then gasket selection, I mean, how is it selected for a joint design? I mean, from our standpoint, what we do is we go through these steps. I don't want to spend a lot of time on this, but obviously we're looking at the joint. We're selecting a gasket or multiple gaskets that'll work. We can come up with which profile and then what volume will then work with that gasket or that joint, and then calculate the stretch on it, and then we get that out to our customer. So fairly simple process. I mean, I make it sound maybe more simple than it really is, but it really is from our standpoint relatively simple. So gasket material, and there are a variety of different materials out there. We primarily use maybe 3 or 4 of them. First question is going to be, is there a specified material? As I mentioned before, if there could be contaminants running through a pipeline or in the ground where the pipe's going to be running, that could mean that you need something that's going to be able to handle something special there. So whether it's alkaline or acid resistance, that would be an EPDM gasket. If you need oil resistance, we prefer nitrile gaskets, but neoprene also works. So there's a variety of different types of gaskets that are available. So it's that's something to check with your salesperson or your supplier to make sure that they can supply what you need. ASTM standards, I think this is very important to cover quickly. ASTM C1619 was developed a few years ago, and now ASTM 361 and C443, which are 2 of the big ones in the pipe industry, as well as C1628, C1677, and others, they now refer to 1619 for gaskets. So they'll still have the performance requirements for the pipe or the structure, but when it comes to the gasket, they'll actually refer to one of the classes of this that's shown in this table for this ASTM standard. So Class A would be C361, Class C would be C443, and so on. I also want to talk just for a moment about gasket quality assurance and why it's important. I think that there's really kind of a slim margin between a watertight joint and a problem in the field. If you have, if the gasket's too small or the joint is not being manufactured within tolerance, then you could have a leak, or vice versa. If the gasket's too big and the joint is also out of tolerance, you could also bust a bell. So we try to find the sweet spot there with making sure the gasket works with the joint, but it is certainly a partnership between the producer of the pipe and the manhole, as well as with the gasket supplier. Making sure that the contractor receives the correct gasket, that's obviously very important. We do our best to make sure our customers receive the right gasket, but nobody is 100% when there are mistakes that can be made. So it is important for the pipe producer to make sure that the gaskets that are being shipped out to the job site are correct. Making sure that the instructions are being supplied to their customer, to the contractor on how to install a gasket. If training is needed, they can work with the gasket supplier on training. And then job site performance, that's going to come down to all these factors. So if the joint performs well, then that works great, and then everybody saves money because it's nobody said to go out and repair anything, and the contractor's happy. Here, just I'm not going to talk too much about these, but here are some of the gasket quality assurance that's done. We do all this ourselves, but in some cases, customers will also do this just to be kind of double check. And then some certification programs require them to do this anyway. But these are just, in order to make sure that the gasket meets those requirements, these are some of the tests. So now let's talk a little bit about rubber properties. Like water, rubber does not compress. So you're not going to see what's happening on the left. You're going to see what happens on the right, where it deforms. You're not going to be able to make that circle smaller. It's only going to make it lopsided. So ASTM C361, the sizing methodology when it was first developed was comparing the gasket volume and then the volume of the total angular space, which is going to be designated here with this pink square, pink rectangle. So within the established parameters the volume of a gasket. So you look at the total volume of the gasket, which is pretty easy with a round O-ring gasket, versus the volume of the groove, which is that pink area, was then they could then determine what the sealing force is going to be. So that's how that was a pretty simple calculation to do. So here you got results for you know the dimensions of the joint, you know the dimensions of the O-ring, and so it's pretty simple. It's a solid shape, and the gasket is confined within that recess. So it's really a fairly simple way to do it. Well, when single offset joint was first coming out, and then we were selling our pre-lubed super seal gasket, we had some issues to overcome with the end users and the specifiers because they're used to being able to calculate very easily what the pressure resistance of that joint's going to be by looking at those two things, the O-ring as well as confined space. Whereas with a single offset joint in this gasket, or even with just a regular profile wedge-shaped gasket, there was not really a way to figure that out. So we came up with a method was developed called deformation modeling in order to calculate what the sealing force of a gasket was in a single offset joint. So I want to talk a little bit about that over the next few slides. We're going to some of it's going to be a little bit on the technical side. We're going to look at some graphs. I'm going to go through it relatively quickly because I don't want to keep you guys all day. But if you have any questions about it, certainly you can ask a question in the question box, or later on, I'll be supplying my email at the end. You can email me. I'm happy to answer those questions. So first of all, deformation testing. So you're basically subjecting a test piece of gasket, to a deformation load. And then what you're doing then is measuring the resistance to that deformation. So you come up with a gasket power, and then measuring the change in height of the test piece that's being deformed, and then you plot a curve. And that's what we're going to be showing here in just a moment is what that curve looks like. But before we get to that, I'm going to show you how it's done. So you can see down the bottom of this is the picture that shows a single offset joint like we've seen already. Well, what we've come up with is a test fixture that looks kind of like what's up at the top. It has walls that are the black part, and then you have a step, which is just like a single offset joint, which is right here. You put the gasket in here, and then you have a load you apply to that. So that pink part is coming down. That's the load that's being applied to that gasket. So here's what our test fixture looks like. You can see that it may not be easy to see, but especially on the picture on the right here, this is where the step is. So here's a step up here, and this is the lower part of where the joint would be. And then you have the block that goes on top with the gasket underneath it. So here we have we can apply a load with this device right here. You put the whole contraption in, and the gasket inside of it, you can see there's a super seal pre-lubed gasket that's inside this, and you put the block on top, and then you apply a load to it. And so this is what a load will look like. Oh, this is what the graph will look like. I'm sorry, when you apply that. So on the left side, you have deformation resistance. So that is going to be the resistance of the gasket to the load that's being applied. And then on the bottom, we're talking about the deformation of the gasket in inches. So as the load is continuing to be applied to it, the deformation increases until you get to a point where the gasket doesn't have anywhere for it to go. So it's starting to max out on the deformation inches, and so therefore the deformation resistance is going way up. So that's the reason you can see this curve, is that you've got a little bit of load, a little bit of deformation, and then all of a sudden it just shoots way up here, and this is the resistance is very high. Okay, so since we're measuring deformation resistance versus deformation, which is the change in the height, the starting height of the gasket is very critical. So there's three factors that are important when we're doing the calculations here, and those are listed here below. The stretch height, that's when the gasket is actually applied on a joint, it's going to be stretched. It could be 10%, 15%, 20%. So there's going to be some stretch to that gasket. So that's going to shorten the height of the gasket a little bit. The effective height, which is going to be the height of when the bell comes over that gasket, what's going to be the height of that gasket. And then you have stress relaxation, which is, we'll talk about here in a moment, but stress relaxation is another factor. So stretch height, the gasket's original profile height will be reduced because of stretching. And then so in order to compensate for the stretch, when we're actually doing the calculations, when we're actually putting the gasket in, so the test tool length from where that step is going to be, so the width of it for the step is 1.453 inches. So if we have a gasket stretch of 20%, that's what the designated stretch is going to be on a gasket for a particular joint. The specimen length then is going to be reduced by 20%. Sorry, so it's going to be calculated times 80%. So you end up with 1.16 inches. So that allows for the gasket to deform to the 20%. So it'll just basically start filling the width of that test tool to compensate for that stretch height. So that's all that's going to be doing. So then you have the effective height. So the gasket, it goes onto the joint. So that's going to be just the height of the gasket without anything being done to it. Then you have another. Then this profile shows with a little bit of stretch to it. And then you have the bell coming over, and that's going to be the effective height. So there's the profile height, the stretch height, and then the effective height. So this curve right here is just showing that the first little bit there, in yellow down at the far left. I'm just going to point that out here. So this little bit right here is going to be showing the stretch. So when the load is first applied to it, it's going to be deforming the gasket a little bit, but that's really just compensating for the stretch. And then the next little bit is going to be compensating for the bell coming over it. So that's going to be the effective height. And then anything beyond that is going to be the deformation. So now I mentioned stress relaxation. So that's what this is. So there's a rubber will relax if a load is applied to it for a constant amount of time, with deformation, and there's going to be some relaxation to basically the power of the gasket. So this is defined by DIN 4060. So the gasket is deformed by 40%, and then the power is measured, just like what we were just showing in that graph. Then it's maintained at 40% for 15 minutes, then the power is remeasured, and then the relaxation factor can be calculated from that. So in this example, the first measurement was 150 foot-pounds. Then the second measurement after the 40% deformation for 15 minutes, it was 135. So then the relaxation factor is 10%. So here's a deformation curve that kind of shows how that works. You can again see the deformation curve. It's going up and up and up until 40% is a 40% load is applied, or 40% reduction rather, and then it's held for 15 minutes, and that starts to drop back down. So the deformation resistance has dropped down from 120 down to 110. So in this case, so in this case, 120 to 110, we calculate that the relaxation of 8.3%. So for the rest of my examples, this is the 8.3% is what we're going to be using. So gasket power, I've mentioned that the gasket power is basically the force resisting the deformation. So as that load is applied to it, that's the resistance to the load. And since we're interested in sealing capability, we need to relate gasket power to hydrostatic water pressure. And so because hydrostatic water pressure is in PSI, we're going to basically convert PSI, or convert the power of gasket power into PSI. So if we have a length and width of a test piece of 1.16 by 1.16, the test strip area is 1.346. And then to get the hydrostatic pressure capability, you take the power divided by the test strip area. So that'll give us the PSI capability of that gasket. So one thing I wanted to point out here is not a word of caution, more of a, this is how we're being more conservative, is that the effective sealing area of a gasket, the sealing surface of a gasket, is not the entire gasket. As this shows, there's a blue arrow, which I'm not sure how clear that is. But from here to here, this is showing what the effective sealing width would probably be. Because as that bell comes over the top of this gasket, it tends to curl this front edge up a little bit. And so your effective sealing width is going to be from here to here, not maybe this last little bit up here in the front. But to be cautious, to be on the conservative side, we're actually use the full width of the gasket because we're dividing by the area. We're actually going to be reducing we're going to be coming up with a smaller number, which is going to be more conservative. So I'll show that to you here in a moment. Okay, so the gasket height, we're going, in this example, is going to be 0.88 inches. And so we're doing a 40% reduction, which is going to be for the, as I mentioned, the stress relaxation. So going down 40% to 0.352. Gasket power was measured at 120 pounds at we're looking at the graph here. So going out to 0.352 here, and going across from this curve over to the other side is about 120 foot-pounds. And so then allowing for stress relaxation of 8.3%, that drops that 120 pounds down to 110 pounds. And then with a test area of 1.346 square inches, then that comes out to 81 psi as the sealing pressure. So now if we had gone with a test strip area, if we'd said that this was going to be, say, 1 by 1, so we're going with a smaller test area, it actually would have made this number bigger. This would have been 110 psi instead of 81 psi. So we're actually being more conservative when we use a smaller square inches for the sealing area of a gasket. So hopefully that makes sense to everybody. Again, if you have any questions, I haven't seen any questions come up yet, but if you have any questions, let me know. So using this deformation model is one thing that's really nice about this is it gives engineers, like the ones we have in our, that work for our company, gives them kind of some leeway in how they can develop, because they can develop a gasket with a variety of different configurations, and it gives them a way that they can then calculate what the deformation, through deformation modeling, what the capability is of handling water pressure. So it really just kind of gives them that, instead of going from a round solid shape or a rectangular or a triangle shaped solid piece, they can go to something that has a notch in it, or they can go to something that's going to have lamels, voids basically running through the gasket. So it opens up some variety of design capability there. So for a wedge-shaped gasket, the total annular space, which I have up here, you can see, total annular space is an important number for us when we're talking about gaskets, because this is the area where the gasket's going to be sitting right in front of the step. So this is the total annular space from spigot to bell. Now this right here is called just annular space, a small area, and that becomes more of a factor for pre-lubed gaskets because that rolling tube rolls in there, but we'll talk about that here in a minute. So you can see down here there's a variety of different types of considerations that go into effect when it comes to figuring out what gasket to use. There's gasket profile height, which there's a min, a nominal, and a max. Same thing with bell diameter, spigot diameter. The stretch height, I mean, there's various factors there. I've listed here that Hamilton can't. We try to stick with a stretch between 17 and 23% for a wedge gasket. C443 allows up to 30%, and C361 is 20% for spigot designs. So there's a lot of different factors when it comes to determining what gasket is going to be the best for a joint. So for us, and what I think our fellow competitors and suppliers, what they try to do is determine the smallest gasket possible to use with a joint, and that way it's going to be the lowest possible cost. That's important for our customers when they're trying to go out and get business. C443 requires that the maximum total annular space, so that's at TAS that's shown up here in the joint, it to be not more than 75% of the minimum gasket height, applied height. So you can't have a gasket that is going to be greater than 75%. I'm sorry, I think I've got that wrong. Anyway, so it can't be more than 75% of the minimum gasket. So it's, if you have a gasket that's 1 inch, the TAS can't be more than 75% of that height. Applied height includes the height reduction from stretch. So as a rule of thumb, we start with about 2 times the normal total annular space. So as an example, if we had a total annular space of 0.326, then a starting point would be a gasket height of about 0.652. And that therefore would be 50% of the total annular space. So that would, I mean, not more than 50% of total annular space. So it's, I think we're in good shape there. So now we need to determine which gasket will meet that sealing requirement. As C443 mentions, pipes in straight alignment require 13 psi of hydrostatic pressure. So for a gasket being considered, you need to calculate the minimum gasket deformation to basically to meet that psi. So we could ignore the stretch height since the deformation curve already includes that. So we have a minimum gasket deformation, which is the height, and then minus the TAS max. So in our example, so we're going to go with a gasket that has a height of 0.600 and then a total angular space of 0.359. So that comes up with 0.241. So that's the minimum gasket deformation. So then we're going to be consulting the deformation curve to find out the deformation resistance at that height. And then we then go to the next step here, which shows what's the pressure, which is equal to the pressure resistance, which is equal to the deformation resistance divided by the test piece area. So just like we did a moment ago. So in this example, though, we're going to go with a test piece of 1.16 inches long, which again compensates for the stretch when it goes into our device for measuring. And then it's going to be then a width of 0.92, so a total square inches of 1.067. So when we run the deformation curve, again, we're looking for a deformation of 0.241. So if you look at our chart here, 0.241 comes out to about 50. It shows on the chart, but it actually was 45 foot-pounds. So then you take that times 0.917, which is taking out the stress relaxation. So then you have a total foot-pounds power of 41.26, which is right here. So then you have a gasket area, 1.067, and you divide the power with the stress relaxation on it, divided by square inches, and it gives you 38 psi of sealing capacity, which, with being a requirement of 13 psi, that gives you a safety factor of 292%. So this gasket in this case would easily, or in theory, should easily meet the 13 psi requirement of C4430. Now, obviously, in theory is what we want to meet when we're calculating it, and then we want to have our customers actually do the testing at their plant. So this is just the first step of meeting the requirements. Then for us, as far as gasket sizing goes, and this is the step we'll go through then as we calculate the cut length. So we look at the spigot circumference, 1 plus the stretch, which then comes to a cut length of we have 21.01 is the circumference of the is the radius. I'm sorry, the diameter times pi, and then divided by 1 plus 0.2, which is going to be the stretch. So that comes up to equal to 55 inches, which would be the cut length on that gasket. So again, circumference 21.01 is the diameter times pi divided by 1 plus 0.2 for the stretch, which is 20%. Is how you come up with that cut length. So that's how we would then calculate what gasket would need to be sent to our customer in order to meet C443 in this case. Just to add a little bit more to that, C443 also requires that one side of the joint be opened up a half an inch for deflection testing. So that also then needs to be calculated. So here's just showing an example of that. So as the joint is opened slightly on one side, the bell is going to be pulling slightly away from the spigot. So that's going to be shown here. So you have the movement, and then you have, so this is the increased gap. So originally, if the original gap was here, then it's gone out to here. So this is the spigot moving away from the bell. So now the step is going to be here, and this is going to be the new height. So the gap increase is going to be there. So in order to calculate that, it's basically taking, well, this is a calculation. I don't need to go through it too much, but the gap increases a half an inch times tangent times 2, or tangent 2 equals half inch times 0.035. So the gap increase here was 0.018 inches. And ASTM C443 also requires testing with that deflection of 10 psi. So that's what we're going to be checking for is 0.018 less deformation to resist 10 psi of hydrostatic pressure. So we go back to our curve, and you can see up here on the top we've taken 0.241 minus the 0.018, which is the increase gap. So you got to go to 2.223. So then that drops us down on our curve. That's, you know, I apologize that these lines are not 100% accurate, but it's going to drop us down to about 35 foot-pounds. Then you take 35 foot-pounds times the 0.916 and 0.917 for the stress relaxation, and that comes up to 32.1 foot-pounds of power. Again, the gasket area is the same. Do the calculation to 30 psi, and 30 divided by 10 for the required psi for C443, and that comes up to 300% safety factor. So again, that gasket should, in theory, work out very, very well for that particular joint. So one thing I've noted here is that ASTM C443 does not consider the maximum deformation. So the largest gasket and the smallest total linear space. Pardon me. So, you know, too much deformation, you know, is going to be a bad thing as much as too little deformation. So too much deformation could result in higher insertion forces because you're basically trying to put a bigger gasket into a smaller area, and that will create much more resistance to that joint being able to close. And we see that sometimes, you know, where, you know, if a gasket is, if there's an issue with the gasket or an issue with the joint, contractors trying to force it home, you know, to force a piece of pipe home or force a piece of manhole down, and that's what's going to happen is just a higher resistance and then potentially bell breakage. That happens frequently when this occurrence takes place. So we try to limit our max deformation to 65%. So in our example here, we had 0.326 minus 0.033 equals 0.293. Maximum, or the height of the profile, 0.63. The deformation is about 54%. So that's the number we come up with down here. So about 54% deformation, which is right where we like to be, a little bit below 65%. So now let's talk just briefly about pre-lubed gaskets. Very similar concept, and the calculations are the same. I'm not going to go through deformation modeling with pre-lubed gaskets because it's very similar. But one thing I did want to point out is that the rolling tube, there's two things that need to be careful of. Number one is make sure you have an annular space, which is the small space here, is big enough to handle the rolling tube. So you have to have at least 2 times the tube thickness. That's what we mentioned here. So at least 2 times the tube thickness of this space right here in order to accommodate a rolling tube. And then you have to have movement has to be enough to allow sufficient roll of the tube. So when the bell comes over, it has to catch that tube and roll it enough that it's the proper amount. So that's we have a wide variety of different types of profiles for super seal gaskets so that we can accommodate virtually any type of joint design. Now, there are a few that we run into where the annular space is not quite big enough. That is kind of a rare occurrence, but that does happen. But that's about the only limiting factor that we found so far with our super seal gasket. So rolling tube will certainly have an impact on differential loading because that, as you can see from the picture here, is that tube, with it being in that annular space, it actually is going to provide a bit of a cushion between the bell and the spigot. So as a load is applied, you know, either to the piece of pipe on the left, could be over here on this side, or to the piece on the right, that gasket is going to actually help prevent that joint from opening as much as it possibly could if it had just a regular lead-shaped gasket in here. Just because that tube is just going to, as we mentioned before, you can't compress rubber, you can only deform it. So there's only so much deforming you can do to the rubber, and then it's going to resist that. And so the bell can only deflect an amount equal to the annular space, which is 2 times, right, equal to 2 times the tube thickness. Well, we have an asterisk there, which I think is important to note, is that, you know, while in theory it would be 2 times the thickness of that rolling tube, it really is going to be about 2/3 of that, so about 1.33 times the tube thickness, because there is going to be some deformation of that tube within that joint. So the same joint can be used for a wedge-shaped gasket, for a pre-lubed gasket. So there's really not a lot of limitation there, other than what I mentioned before about the annular space, that smaller space, if that will prevent a rolling tube from going into it. But we think that the rolling tube provides a lot of benefit. It helps to kind of lock the joint together because it has little teeth inside that kind of lock it from kicking back. It also helps with the differential loading, as I mentioned before, because that rolling tube will act as a cushion. But then, in addition to that, the concrete-to-concrete contact, when you're just even homing pipe, that rolling tube will help to prevent any damage to the concrete when that homing is taking place. Just a few notes here on gaskets for field application. We certainly recommend that good installation techniques be used, and I think that most pipe producers, most manhole producers, they have, they know what good installation techniques are, and I think most contractors do too. But there are some contractors out there that may not choose to use the proper techniques as far as how to lower the pipe into the trench, how to home it, how to lube. Are they equalizing gaskets if they're required to? So some of those things that maybe they're not doing quite right. And I think it's important that if a representative of the producer can't be there to make sure that the contractor's doing things right, then at least there's somebody from the engineering firms that's there to kind of keep an eye occasionally on the installation process. Cold weather installation. Gaskets in general are going to be fairly similar in durometer, which is the hardness, but when it's exposed to cold weather, rubber will get harder. And I think that probably is pretty intuitive that things that get colder, they get harder. So that's something to keep in consideration if you're doing a project where it's going to be in a very, very cold environment. That gasket is going to be harder to put on the spigot. It's going to be the insertion force is going to be harder. So one thing that can be done in order to simplify that a little bit is to to put it in the bed of, put it in the cab of a truck or a piece of machinery that has some heat, so you can keep the gaskets warmer. That'll help alleviate some of those issues. Again, what to watch out for: pipe and manhole installation. That's certainly going to be, as I mentioned before, something important. If gaskets are actually coming off of a spigot, and are they being cleaned? Are they being wiped off before they put back on? Because that's certainly going to be make an impact. Because a dirty gasket on a joint is going to be an impediment for it to be to homing correctly. And then is there damage to structures or pipe at the job site because of handling? We've heard all kinds of stories of using a lifting hole on a manhole to use that to drag it across a job site, or rolling pipe, with a piece of machinery, rolling it across a job site. So there's things that we see and we hear about handling that can have a big impact on the structure itself, as well as on the joints. If they break off a spigot, obviously a gasket's not going to work on it, and that's going to create a big issue when it comes to sealing capacity. And then the final note I have here is just get your supplier involved. I mean, if you're a producer of concrete pipe or manholes on the call, then certainly get your gasket producer involved if necessary. If you're a contractor or engineer or municipality that's on this call, we certainly encourage you to get your supplier of concrete products involved. I think that's just the more you can partner, I think the better off you're going to be. And I mentioned this just a moment ago about pipe installation. And here's what I think is a good installation. So you can see the pipe is coming in, it's being lowered into place. Well, that's actually got a little bit too close, but right there you can see it's lowered into place pretty much right by the bell. You can see right there's a little bit of a gap between the bell and the spigot. And then they use the chain and the track code there to then just pull it together. So it's come together nice and level, and that's the way to do it. Unfortunately, we see too many times where a contractor will actually bring a pipe in at an angle. They'll they put the spigot inside the bell end, and then they'll drop the bell end of the other pipe down, and the gasket actually gets knocked off. And they don't even see that, and they try to home the pipe together, and it either busts the bell or you have a gasket hanging across the pipe, and then you have a leakage there. So that's unfortunately something that we see too much. So just to kind of in summary, certainly we recognize there are a lot of challenges going on right now with our infrastructure. We have a big deficit. the lack of funding currently. So there's and just a lot of failures. We're seeing a lot of pipelines fail, a lot of bridges and roads and much more. So there's big challenges with infrastructure. So with that happening, municipalities and consulting engineers are becoming more cautious about what's being installed on the roads, how it's being installed, how long it's going to last, and which I think is a very good thing. So they're taking more of a long-range approach to everything, whereas instead of taking just what's the cheapest thing we can put in the ground. There's a broad variety of gaskets for concrete pipe, for concrete box culvert, manholes, other types of structures. It's a broad variety of different types of gaskets out there, available in a variety of different types of rubber materials to meet the requirements for a job site. And then deformation modeling, which provides a really good gasket selection process, as well as a good tool for companies like us to design gaskets to be able to fit with a joint. And then finally, just as we just touched base on, was the proper gasket installation and field techniques. Certainly those are going to be very important when it comes to the final use of the pipe and the final use of the gasket out there at the job site. So with that, I'll first want to thank you, and second want to say, do you have any questions? Because certainly we have a couple minutes here. That took us just right about an hour. So if you have any questions, please type them in. There's a question box in your GoToMeeting menu bar there. I also wanted to, while we're waiting for anybody to type any messages, I wanted to let you know that if you would like a PDH certificate for the session, I'm happy to send that to you. My email address is listed at the bottom there. That's my first name dot last name at hamiltonkent.com. So just feel free to email me, and I'll get that sent out to you here in the next couple of days. We also encourage you to connect with us on LinkedIn, on Twitter, on Facebook. We're constantly posting information about our products, about projects, about infrastructure. I mean, just a lot of information. And if you're not receiving our newsletter, email me, and I'll make sure you get on our newsletter list, because we send out a monthly newsletter. I think it's really good. And my phone number's there as well, just in case you need to call me. Okay, so any questions out there? Okay, I have one question here that came through. It's on gaskets for box culverts. And well, it's not a very specific question, just what gaskets are available for box culvert. And I'll say that for the typical typical box culvert, that's going to be a tongue and groove joint. If it has a slope of less than 5 degrees or less on the joint, then you can use, we have a gasket that we've manufactured that actually will work with that. It has a molded corner so that you can actually glue it on the spigot, and then you can use that as to seal up a box culvert or any type of square or rectangular shape of structure. But when it comes to other types of gaskets, the only way to really do that is to go with a single offset joint, and then with rounded corners, with a 6 or 8 inch radius corner. And that opens up the possibility of using like a pre-lubricated super seal gasket or other type of profile gasket. The tolerances on that are much tighter, but that would be the option. And we're seeing more and more gasket boxes being used all over the country. I've got another question here. Do you consider the 1/2 inch joint deflection on one side the same as a 1/2 inch gap all around? Yeah, I would say that would be the case. I mean, the C443 does require a 1/2 inch on one side and not the other. But when you're talking about the amount of pressure on the gasket between the bell and the gasket, you're going to be talking about basically the same deformation of the gasket all the way around the joint. So it should be identical, whether you're opening a 1/2 inch on one side or 1/2 inch on both sides. So it should be about the same. Are there any other questions that anybody has? If you don't have any questions right now, if you want to email me those questions, I'm happy to answer those then, or call me. But I do appreciate everybody being on the call, and certainly want to encourage you to continue to check in with us. We'll have another webinar here coming up soon, and we'd love to have you on there. So with that, have a great afternoon. Thanks, everyone.